right, we are going to do a practice problem using our information about electric potential and kinetic energy and electric potential energy, and looking at a situation where a proton is initially at rest 0.25 meters from a stationary charge Q. Charge Q is 0.85 nanocoulombs, and of course the proton has a charge of 1.602 times 10 to the minus 19th coulombs. And if we release that proton, it's going to be shot away from this positive charge. Positives repel each other, it's going to be shot away from this charge. The question is how fast is it moving really, really far away? Okay, so how fast is it moving really, really far away? Now when we think about analyzing how fast something is moving, we can do it in a number of ways. We can look at kinematics and forces, or we can look at energy. And we're going to look at energy in this example because we can talk about the electric potential energy of this charge when it is at a certain distance away from that source charge. Okay, so if we're thinking about energy and we're thinking about motion, because I want to know how fast it's going really, really far away, we're going to think about kinetic energy. And we know that the change in kinetic energy is equal to minus the change in a particle's potential energy. That's our conservation of energy idea when we don't have any external forces acting. So we're going to use this idea to solve this problem. Let's start with the potential energy of this particle. We've learned that the electric potential energy is equal to minus the charge times the electric field times the distance that charge is located, okay? So we have this relationship of electric field and the distance, right? So what is that electric field? Well, the electric field that particle, this proton, is experiencing is due to this point charge. So we need to determine the electric field of that point charge. So the electric field of the point charge, remember, is K times the charge Q over R squared. So we know that K is, of course, 8.99 times 10 to the 9th. Q is 0.085 times 10 to the negative 9th nanocoulombs, all over our distance R, which is 0.25 quantity squared. And when I calculate that, we find that the electric field at this point in space, due to this stationary charge, is 12.23 newtons per coulomb. All right, so we're going to need to know the electric field. What if we are interested in the kinetic energy, and the kinetic energy is equal to negative the change in potential energy, then if our kinetic energy, or change in kinetic energy, is equal to minus our change in potential energy, which is equal to minus our minus Q E D, then we get our change in kinetic energy equal to Q times the electric field that Q is experiencing times D. And that distance being our 0.25 meters. So our change in kinetic energy, our kinetic energy final, minus our kinetic energy initial, is going to equal Q times our electric field times that distance D. Now our infinity potential is 0, so we don't have to worry about the potential at infinity. So our initial kinetic energy we know is equal to 0 because the particle starts at rest. So we get kinetic energy final is equal to Q E times D, which is going to give us Q is our proton, 1.602 times 10 to the minus 19th, our electric field of 12.23, our distance of 0.25. All right, so that gives us a final kinetic energy of 4.89 7 times 10 to the minus 19th joules. All right, so we know our kinetic energy. Now, how do I get my speed from kinetic energy? We know that kinetic energy is equal to 1/2 mv squared. So our kinetic energy is equal to 1/2 mv squared. So that now is going to equal 4.897 times 10 to the minus 19th. I can solve for v. I get v is going to equal this, v, our velocity. V is equal to the square root of 4.897 times 10 to the negative 19th times 2, all over the mass of my proton, which is 1.67 times 10 to the minus 27 kilograms. And I solve for v. We get v equal to 2.4 times 10 to the 4th meters per second. All right, so looking at our relationship for kinetic energy, our understanding that it takes work to get this change in potential energy, and that work is given by the relationship we learned about previously in terms of particles' electric field and where it's in that electric field in a situation like this. And we can use both that piece of information to solve for velocity. Good job.